Okay, so we're back after a brief interruption forgot to zoom over, and the board is not I'm not able to zoom in and cover all the boards, so I apologize for that. We'll just start here again. We started off with we write AB for A times B, A star B with a binary operator group. And then if there's a property that AB equals BA, we say that group is abelian. And we have this matrix ring here, this matrix group, has AB on the top entry integers with A being plus or minus 1 and 0, 1 in the bottom row. So we'll give you a moment to look at that. This example I actually talked about after the example with D. Then I'll scroll over. And we'll maybe zoom out a bit to get some of the examples I mentioned. And again, we've just sort of talked at these notations. I've just written in set notation as I write it up. Parentheses, the group, comma, the operation. So most of the familiar number systems are groups under addition, that plus sign. Multiplication, certainly Z is not a group. There are not inverses for any elements except 1 and negative 1 on the multiplication. The irrational numbers, they do have inverses, but not for all elements. There is no inverse for 0. So that is not a group. But if we look at the non-zero rational numbers, that's a group under multiplication. That's what this X stands for, multiplication. And similarly, the rational numbers, the real numbers are a group under multiplication. And in all these groups, the example, we had A times B is B minus A. And then on the previous board, we defined that as a abelian. So then we looked at the set D, and I claimed D is a group. D, that was on the previous board, but it's a matrix of the form A, B, where A is and B are integers, and A prime and A is plus or minus 1. So again, those 4 elements are integers, and A prime is plus or minus 1. And I multiply them out, and as we saw, you get this entry as A prime, that's plus or minus 1, and that's an integer. So that would be an element of D. So let us move on to the next board. So, I've got to move this here. We can zoom in. And we've got it right there. We can maybe even move my line a little bit over. And we'll continue to show that this group D is, well, this set D with the matrix multiplication is a group. So we have that what about the inverse? Well, what is it equal to? It's 1 over, what's the determinant of this? So it's 1 over the determinant, so A times 1 minus 0 times B, with just A. And then that's multiplied, these switch here, and we would have a 1, an A, a 0, and a minus B. Which is 1 over A minus B, 0 over A over 1 times A would just be B. So that would be minus B over A over A. And this is in D. Since if A is plus or minus 1, the reciprocal of 1 is 1, the reciprocal of minus 1 is 1, so the reciprocal would be plus or minus 1. So it has an inverse. What about the identity? We should say, well, what is this equal? So that's would be an A, and we already know that this product has to be the identity. We should show that the identity is in A, but we've seen in our notes on matrix is in D. The identity matrix fits into D because 0 is an integer and 1, the top entry could be plus or minus 1. So we do have that. But D is not abelian. And we can check that in a whole bunch of ways, maybe 0, 1, 0, 1. Well, that's the identity, so that will work. So I think if we put maybe a 1 here, and then put a, probably should just stick with the example I did in the class, but maybe a negative 1, 0, 0, 1. So this would give us a negative 1 here. 1 times negative 1 plus 1 times 0 would give us negative 1 plus 0, negative 1. 0 plus 1 would give us a 1. And this would just give us that here. But if we switch the order, this would give us negative 1, negative 1. And these two are not equal. So D is a group, it is not an abelian group. Okay, then we'll prove kind of sort of basic facts about groups that come from the property. A nice use of proving something. So we start off with in a group, the identity is unique. So the proof, we let E and E prime both be identities. So there are two different identities. Then what do we have? Then E is equal to E times E prime, because we can multiply E on the right by that identity E prime. But E is a left identity. We can multiply on the left. We can multiply E prime on the left by E, and that would keep it at E prime. So again, it looks like I pulled a fast one. That first inequality, I'm taking E and I'm multiplying it on the right by the identity E prime. So that's going to equal E is E times E prime. But I can also view E times E prime as I take the element E prime and I multiply it on the left by the identity E, and that would keep it at E prime by the left identity would give us E prime. And so that proves it, right? So the identity is unique. And the second identity, it's in fact equal to the first identity. So we'll prove another theorem along this type. And that's cancellation. Before I do that, let me make just a sort of a fact. It's just because of the associativity, we can write A, B, C because of associativity. Where A, B, and C are elements of G. So that's one sort of consequence of associativity. We can just say, if we have three elements, A, B, C, and G, do we mean this, or do we mean that? Right? If we see three numbers, really we can only multiply two numbers, so which is it? But because of associativity, it doesn't matter, the result's the same. So we just write A, B, C. Anyway, this is more sort of DVD extras, as I like to call them. I don't think I mentioned this in the notes. That one of the basic fact of associativity that allows you to get away with not having to put parentheses. So certainly this is true in real numbers, right? You can only multiply two numbers, but I mean, you don't use parentheses that often. 5 times 3 times 8. You wouldn't write it with parentheses because the associativity says it doesn't matter which way you perform the multiplication. So another theorem along the lines of that last one is going to be, in a group there are left and right cancellations. Given a group G for any A, B, C, and G, if AB equals AC, then B equals C, and if BA equals CA, then B equals C. So you can see why this is kind of called cancellation. You can just cancel the A on either side. Proof. We only prove right cancellation. The proof of left cancellation is similar, and also is similar, and that's the one I actually did in the notes. So we assume BA equals CA. Let X be the inverse of A. Such an element exists because we have a group. then if we multiply this equation, we would have on the right by x, BA times x is equal to CA times x. We use associativity, that gives us B times AC, AX is equal to C times AX. But then AX, if X is the inverse of A, AX is the identity. So that becomes BE equals CE, or B equals C as required. And so that completes the proof of right cancellation. Okay, the next theorem, the identity is unique. How about inverses? In a group, the inverse of any element is unique. So let's prove this. Let A be an element of G, and suppose B and C are two inverses of A. What does unique mean? It means they're not really two different ones, they're the same one. A would equal C, B would equal C. So what we do is we have AB equals E and AC equals E. Well, that allows us to say that hence AB equals AC using left cancellation. We get B equals C as required. And so now, because there's an identity unique, given G and G, we denote the inverse of G by G inverse. Well, is the inverse of G inverse equal to G? And that would be an emphatic yes, right? G inverse times G is the identity, and G times G inverse is the identity. So if I multiply G inverse on the right by G, that gives me the identity. Same if I multiply G inverse on the left by G, that gives me the identity. So G inverse is just G. And so in some ways, in keeping track, even in an abstract group, we can use some of the properties of exponents. So we define if n is greater than or equal to 1 and an integer. Well, let's just maybe start with n an integer. So we have any integer g to the, what we define when n is greater than or equal to 1, g to the n is the product of g n times. When n is negative, define g to the n as g inverse to the negative n. G inverse is an element of g. If n is negative, negative n is positive, and since n is strictly negative, it'll be greater than or equal to 1. So we use this definition here. And the same way x to the 0 is often defined to be 1, that's for x not equal to 0, we would define g to the 0 as the identity. So maybe let me erase this. I just said set g to the 0 equal to the identity, but that kind of got put over here with the n times. We set g to the 0 equals e. So sometimes in our calculations, the familiar properties of x, some of the properties of exponents apply. We have to be careful because we've seen the commutative law may not hold for in a group. You may have a non-abelian group, a group that is not abelian. Whereas the numbers we usually work with powers of the real numbers or variables. We're often in algebra working with real numbers. So in that case, there's some additional properties of exponents that involve, use the commutative property of numbers. See that line? Yep. Okay. So I think I made one of the notes. We just have g to the n times g to the m. You would add exponents. You would multiply exponents if you raise them. Okay, what else have we noticed for? What about the number of elements in each group? The few examples I've looked at, that matrix and the number systems, all have infinitely many numbers. What about a finite group? So let's take one example. So now let G be 1, -1, I, -I, under multiplication of complex numbers. One can show G is a group of 4 elements. And the way you can do that is to put a Cayley table. That's just a multiplication table for the groups. So once we do this column, we can see that 1 is a identity if we multiply on the left. So what we want to put here is, think of A and B. This element, we put A times B in that slot. And then this would be negative 1. Negative 1 times 1 is positive 1. And then I, again, this should just be the same. I times negative 1 is negative 1. I times I is I squared. That's negative 1. I times negative I is 1 over I is negative I squared, which is negative of negative 1, which is positive 1. And we've seen I times I. Let's see, this is, oh, this should be negative I here. So again, those are I's. So you notice this is like an example of a Sudoku puzzle. If we go down each row and each column, there are no repeated entries. It certainly is closed, right? We see everywhere we multiply, we only end up with these 4 numbers are the only ones that appear. We've got an identity. 1 is the identity of the multiplication. The inverse of the identity is 1. Negative 1 times negative 1 is 1, so the inverse of negative 1 is negative 1. I times negative I is 1, so the inverse of I is negative I, and that same calculation shows us the inverse of negative I is I. So all elements have its inverse. Is it associative? Well, we'll take that again as a property of complex numbers. So in a Cayley table, no repeats in a row or column. And how can we see that? Suppose you had some Cayley table, and suppose these two were repeats. So here's B, and here's C. And this is some element A, so this would mean BA is repeated as CA. So if it's a repeat, means BA equals CA, but we can cancel in a group that's cancellation, so in fact, B and C would have to be the same. And the way a Cayley table is set up, you put different elements down each row and each column, so if you're in different columns, you have to have different elements labeled. So again, I tried to prove that in the notes. That's maybe a little bit hard to see, kind of thinking visual, whatever this entry is. You match these two up, if these two are the same. So there's a group of 4 elements. Is it abelian? And it is abelian. You can see that if you look at a diagonal, abelian group, the Cayley table is symmetric about the diagonal. Right? Because if you take the ith row and the jth column, that's going to be the ith jth entry. If it's abelian, you can switch the order, so you can take the jth row and the ith column, that would be the jth entry. And if it's abelian, those two are the same. And so you've got that symmetry about the diagonal. So it is symmetric. And this leads us now to leads us to a, what am I trying to say? I don't know. We'll find out while I erase. I know what it does. It leads us to a definition. The definition is the number of elements in each group. We give that a name, we call that an order of a group. So we define the order of a group G to be the number of elements in the group. And what's the symbol? They actually use absolute value. They put those bars on it. We denote, well, I should say first is the order of G by that symbol. We denote the order of G by that symbol. And if this order is finite, if it's less than infinity, we say G is a finite group. So one thing, let's look at what the possible Cayley tables are. So some of these are in the notes. The one element group, you could just have the identity times the identity. So I have to give you E, so that's a group. What's an example of this? If we just look at the set 1 under multiplication. Or G could be 0 under addition. And these, we'll get into this in a deeper concept here, but in some ways those would be the same. They look like a Cayley table. It's almost like if you took a paintbrush and you, instead of E, you wrote 1, you'd have, and said multiplication, that would be one group. If you wrote 0 instead of E and said addition, that would be a different group, but it's really the same group. So that's what we're going to go through now, look at the different ways to make a Cayley table. What about a 2-element group? So it's got the identity, and it's got some other element that's not the identity, A. And so we have to have E times E of E, E times A. Down the top row and the leftmost column always has to be identical. So the first row is the same as the leftmost column. The first column is the same as the leftmost column. The first row in the table itself is the same as the top row. And then what's here, the only way they complete it, this has to be a different number. So if it's an A here, it's got to be an E. And that works. How about an example? How about 1 and -1 under multiplication? So we've got a 1-element group that looks like that. Is this abelian? And yes, it is. Obviously, 2-element group has to be abelian because there's only E and A. EA is equal to AE. That's one of the group properties, the so-called axioms of a group. And then A times A is the same thing as A times A, so you've got all those covered. What about a 3-element group? Suppose you have the identity and an A and a B. And as before, the top row and the first column are the same as the label and row and column. Then what could A times A be? could it be E? Could we put an E there? That wouldn't do it, because if we put an E there, B has to go in this slot, and that's not going to happen. So it has to be a B. And then the only thing left here is a C. But what about here? That would leave a E here. And then BE is only would be A. So what's an example of this? And so what you have is I'll take a matrix, the identity matrix, a matrix 0, 1 in the top row, negative 1 in the bottom row. And then this matrix under multiplication. Does this work? And if we call this would be our E, A, and B. Well, certainly we know we're on the identity, so A times B would give us, the top row would be 0, 1, or 1, 0. And then this entry here would be negative 1 times negative 1 plus negative 1 times positive 1 would give us the 0. Then this against this row would give us a positive 1 and a 0 in this entry, so there'd be a 0 there. Have I gotten what would be in this entry? This would give us 0 times negative 1 plus 1 times 1. That should give us, let's see, AB. Oh, where's C coming from? AB. This is E. So maybe let me make that calculation. So let me try to talk this through before I write it again. If I'm taking A times B, the top entry here would be 0 plus 1, so I get the 1 here. Then this entry would be 0 plus 0, so I get the 0 there. And this entry would be positive 1, minus 1, give us 0, and positive 1 plus 0 will give us the 1. So these matrices are a concrete example of how you can have an actual mathematical object fill out that Cayley table. In some ways, this is a group, right? I can just define the multiplication for a finite group by explicitly listing the Cayley table. And then we'd also have to check, would B times A, would those two matrices take us back to the identity? So let me work on that. If we see this times this would give us 0 plus 1 minus 1 plus 1, 0 plus 0, 1 plus 0. It would in fact give us the identity. So we're just going through 1 element group, 2 element group, 3 element group, 4 element group. Again, is this one abelian or not? and we look at it, AB is the identity, BA is also the identity. So what about a four-element group? We've got a Cayley table there. If we want to set it up, maybe E, A, B, C. How can we complete it? Four-element order G equals 4. Is that the only possible group? So I should make the comment that those show that those are the only possible group. There's no other way I can fill out the Cayley table. There's no choice involved. So what about here? And so if A is like 1, 1 times 1, we put a, well, E is like 1, A is like -1, so we put a 1 here. And then if B is your I, C is like a negative I, so that would be, well, I'm sorry, 1 is the identity is E. And then negative I, that's kind of what I'm labeling as one, A is -1, B is I, C is -1, C is negative I. So this would just be C, that's B here, then B times A would, again, here would be C, which would leave this as A, and that as B, and then this would just be C would be let's see, that would be C, this would be B, that would be E, and that's left in A. So that's one Cayley table. Is that the only possible way? And so it turns out there's not. There's a degree of choice in completing this table. So let's look. So the first row and the first column are automatic. Then what if instead of here, okay, I put an E here, so that's okay. And then I can put a C here. And then a B there. But now over here, suppose instead of putting a C, what could I put? Well, let's see. What if I put an E here? I mean, what could go here? Certainly, in this here, I can't put a B, and I can't put an A. So I could put a C. And then this could still be an A. I basically swap those two. Will that allow me to be a Cayley table? Well, that leaves B here. I think good with repeats. So far, so good. And here's an A here. Again, good with repeats this way, and so far, so good. That forces E, but we've completed. So it's sort of a different Cayley table. So these, as we'll make formal later in the course, are different groups. is this group abelian? I think if you look at the symmetry, it is abelian. But this one has the property that a squared is the identity, b squared is the identity, c squared is the identity. So this group, if it exists, I mean, I guess it exists in abstract symbols, we've completed the table, but how can we realize it as a more familiar object? And we'll come back to that at the end of the lecture on group. So this group is defined by the property of a squared equals e. I think what that really means is this means every element is its own inverse. Right? Because if a squared is equal to e, but a is squared is a times a. So if you multiply, what do you have to multiply a by to get back to the identity? Just a. All right, this group, again, it's certainly, maybe we can realize it in another way, but this is sometimes called the Klein 4 group. So it's a 4-element group where every element is its own inverse. Here, this is not the case, right? In the concrete example we looked here with i's, b squared is a, or I squared is not the identity, I squared is negative 1. My line, C. I use the same line. Okay, so kind of led to two questions. First of all, question 1. Given a positive integer, is there a group G with n elements? And question 2, is every group abelian? Because so far, have I shown you an answer that, and, or let me actually say, is every, that we know is no. But how about the finite examples? Is any finite group abelian? So let's start with question 2. So let G be the following matrices. What I'll call A, C, then B is a matrix that we previously used before. C I've already given. D we've also used before in the example of a group with 3 elements. K, and finally I, the identity element. And again, that's under matrix multiplication. And again, we recall that I, B, and D, those 3 elements themselves formed a group of 3 elements, and that group was abelian. So G is a non-abelian group. And again, the Cayley table, we can put it up here. These are right in the notes there. You can see, if you go through this multiplication, this does meet a Cayley table. It has a property down, pick a column, no repeats, pick a row. Oop. How about this? And pick a column, no repeats, pick a row, no repeats. And again, I think it can be non-abelian. Well, definitely we want to show why B and D commute, but what about B and C, or even A and B? So if we look at A times B, that would give us a 0 up there. And it's got 4 other entries. We can probably figure them out. That would give us a 0 here, a -1, and a, see, that would be, oh, I'm sorry, I miswrote A. A would be a 0, 1. So that would give us -1, -1, -1, and 0, which is the matrix we call D. How about the other one? Will this be a lucky winner, or will I have to go back and make another calculation? So this would give us a positive 1. Okay, so right there we know they can't be the same matrix. And a positive 1, and a -1, and a 0, which is one of those matrices, right? That's D, A, B. Or did I miscopy? No, that's K. Let's see, let me make sure that's right. 1, 1, that's fine. For the top row, this would be -1. Oh, this, is this matrix A? All right, yeah, so I've miscopied A yet again. A would look like that. Yeah, I apologize for that. So the other matrices are correct. Again, we've gotten D and B are the same, and the identity are the same as before. And then the matrices we add A, so that was incorrect. That's 0, 1 in the top row, 1, 0 in the bottom row. C has a -1, +1 in the top row, and a 0, -1 in the bottom row. And K has a 1, 0, and a -1 and a -1. And so if we go back and make this calculation, so A times B, so that would put a 0 here. That would not change the top row. But that would change the bottom row. The bottom row would then be 0, 1. So that would be D. Well, that's we perhaps need to see. Maybe this matrix is not a group. Let's see if I'm working off my notes here. These all appear to be labeled correct. If those are not labeled correctly, we would need to do that. I certainly have B and D are correct. They give us the identity. So they're okay, but I think I need to look at these matrices. So we'll come back to this example to see exactly what the 6 matrices should be in that. And we'll have actually another way to do that table. I believe those are correct, but apparently does this violate closure? Oh, here we see this is a -1, so this would be no, that is correct. That would give us that one there. That does not appear to be one of the 6 elements in the group. So we'll come back to this group in a second. We'll actually realize it's Cayley table in a different way. So again, let's go back. We'll correct that board at some point once we straighten out exactly where those matrices, probably a 0 and a -1. One of the matrices I probably had the something incorrectly copied down in my notes. Certainly, it definitely appears to be closure, right? Would be violated. So let's look at another 6-element group that's really the same as this. I just wanted to get it in a different, realize it in a different way. And these are very important groups that we'll come back to quite a bit. So the group we want to look at is the element G. So that's maybe transformations, or really symmetries of an equilateral triangle. Which we may label, and the way I labeled it, I put an A at the top, and then I went clockwise, B and C. And so we have a variety of matrices of ways to look at these things. So what are the elements of the group? So one way of thinking about these is you can think about how they act on a triangle in the end position. So one symmetry is just to do nothing. Take that triangle and just move it like that. We may call that little e. And you can maybe think of this as a rotation if you put a center here by 0 degrees. So sometimes it's denoted r sub 0. Then what we could do is we could rotate it 90, it's an equilateral triangle, so you could have a rotation of a third of a turn, 120 degrees. Take this point and move it there, 120 degrees. So now B would be here, A would be in this spot, B would be there, and C would be here. So you've taken this and you've turned it by that amount. And let's just call this one A. And again, maybe in some notations they might call this R sub 120. It's a 120 degree rotation about a point here. So if I take this and rotate here, that would be 120 degrees, a third of a 360 turn. And another rotation, let's call it B, we could turn this twice. So that would be the A here would be end up over here, and then the B here would be over here, and the C would wrap around in that spot. And you can think of this if you took this about the point, and now you rotated 240 degrees. And incidentally, this is almost the same in some ways as the group of matrices if we think of this as, this was the matrix I, the identity matrix. This could be the matrix B. This could be the matrix, that could be the matrix D, right? B and D were the previous matrix in the group. So is that all the symmetries? Well, we can actually do some reflections as well. You could fix this vertice and reflect about a line through the vertice, that vertice, and that would swap these two. That would now be a B and a C, and that would be A. And I think I called that one, I think I called that one C. But I could also reflect through, keep wanting to label my triangles. I could keep this vertices fixed and flip it around that vertex. Again, a reflection. That would give us that, right? The only symmetries of a regular polygon, you can really have just rotations or reflections. And then finally, if we had A, B, and C, we could keep this vertex fixed and draw the perpendicular line from the vertex to the other side, so the altitude through that vertex, and that would, if we use that as our line of reflection, that would switch these two. You will C, A, B. All right, so then we'll call maybe this other transformation, we'll call that D, and this one F. And so we can do a Cayley table, for instance. What does AC? So first of all, what I claim G is a group under, well, function, you can think of a transformation, so function composition. Or composition of transformations. Okay, so we need to be careful. You might remember from a pre-calculus that the order you compose functions makes a difference. If you have a function f of x equals x plus 1 and g of x equals x squared, f circle g of f might be different from g circle f. So we have to be careful how we define the order of the multiplication in this group. Okay, so first of all, in this group, A times B means first do B, then do A. Now that seems a little strange, but recall that if we have G circle F, F circle G, G is written to the right of F. We apply G first and then apply F to the result. So note, what about the associativity? Really, any sort of function composition is associative. Since what? What did you look at? If you look at F composed with G, composed with, say, H, that would be F composed with G of H of X. Which would be F of G of H of X. And what about the other way? We put the parentheses there, that would be f of g composed with h of x. But by definition of function composition, that's just f of g of h of x. So really, in the nature of function of composition of function, it's associativity. It's sort of one of the essence of how it's defined. Really doesn't matter how you think about doing it, in which order. The order matters, but whether we plug x into g composed with h and then plug that into f, versus first plug x into h and then plug that into f composed with g, we'll get the same result. It's just x goes into h, which then goes into g, and that result then goes into f. What about some multiplication? Let's look at some examples. So what is a times c? So this would mean first do c. So if I take my triangle A, B, C, and so C, if you recall, C was the one that fixed this top vertex. So we flip it, and it would be A, C, B. And then A would then be a rotation clockwise by a third of a turn, 120 degrees. So this is C. Then A would put this A here, C would go here, and B, so it would be AC across the bottom and B at top. And so if you look at what is the net effect, the one to do that, that would be F. Right, really this two-step process is the same as taking this vertex, fixing it, and reflecting these two. What about is it a billion? What about C times A? So we take our equilateral triangle, and now first A is, we go from the right, we do A first, so we turn it 120 degrees, that would give us A, B, and C. And then over here, we reflect, A is a reflection through this top vertex, which is now labeled C. We would flip these two, and we'd have B, A, and the top vertex C would still be fixed. So which one is that? The net of, you know, looking either at the table, this looks out to be D. The net effect is to treat it as a reflection, keeping this vertex fixed, and flipping those. So this is not abelian. Is it a group? I've included the Cayley table in the notes. And you can see, or maybe you can't because of the zoom feature, but there are no repeats. It is in a non-abelian group. Again, notice how it's not symmetric here. This thing, if I flip it over the diagonal, it's a different entry. It does not match up. So that's essentially this table that can be realized as a group of 6 matrices, and we'll come back to what those 6 matrices are. So we've answered question 2 first. Not every finite group is abelian. And this 6-element group of the symmetries, the geometric transformations of an equilateral triangles that are symmetries, do not change the shape of the object. is an example. So what I'd like to do now is create an answer to the first question. If you give me a finite number, can I give you a group that has that many elements? And so for that, there's several ways of doing it. One of it actually makes notion of this mathematical idea called an equivalence relation, which we'll get to that shortly. But the way I'm going to do it, I'm going to stick with an existing number system, the complex numbers. So we now answer, is there a group of any finite order n? So what we want to do is we want to let G be the cosine of 2 pi k over n plus I times the sine of 2 pi k over n, where k is 0, 1, all the way up to n minus 1. So certainly G has at most n elements, right? 1 to n minus 1 is n minus 1 elements, but then we have 0 there. And we can also, shorthand notation, we say e to the I 2 pi k n. I'll probably need to write my subscripts a little bit bigger. So G equals e to 2 pi k n times I. So I claim G is a group under complex multiplication or multiplication of complex numbers with the order of G equaling n. So that answers an affirmative. Our first question. Once we define an order of the group, can we always construct a group with that many elements? And the answer is yes. So as usual, we just take the associativity to be given. Actually, it's not a bad exercise to prove the associativity of complex numbers using the associativity of real numbers. But that's sort of a property of the real numbers, the associative property of multiplication. Now let's just look at an example. Remember, I'll recall our 4-element group. This was it. Right? If you look at n equals 4, the cosine of, well, if I plug in k equals 0, I have cosine of 0 plus I sine of 0. The sine of 0 is 0, the cosine of 0 is 1. When k is 1, this would be 2 times 1, 2 pi over 4, or pi over 2. So cosine pi over 2 plus I sine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so it's just I. When k equals 2, 2 pi times 2 is 4 pi over 4 would just be pi. So cosine of pi plus I sine of pi. But the cosine of pi is negative 1 and the sine of pi is 0. And finally, when I plug in n minus 1, 3, I get 2 pi times 3 is 6. 6 pi over 4, or 3 pi over 2. Cosine of 3 pi over 2 plus I sine of 3 pi over 2. But the cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is negative 1. So I just get negative I. So the four-element group that had 1, I, negative 1, and negative I is in fact created this way. What does the set look like? If we think about the complex plane, if we have the unit circle, what these numbers are, in degree, instead of radian, it would be 360 degrees over n. And then another 360 degrees over n. So these are represented as points about the unit circle that start with a rotation of 2 pi over n, or 360 over n. So again, in the example of n equals 4, you've got a 90-degree rotation. So the four elements are negative I, negative 1, negative I, and then 1 itself. So let's try to show closure. Again, the way you would multiply complex numbers, remember, we've seen that's the same as adding the angles. So if you think about how would any two of these add, if we just add the amount, we get another one. So let's show closure. So if we look, let k and k prime be numbers from 1 to n minus 1. If we look at e to the I, 2 pi over nk times e to the I, 2 pi over n times k prime. Well, we've seen the complex, because of the way the trig identities work on our unit on complex numbers, we've proven that to multiply complex numbers in polar form, you would just add the angles and then multiply the radius. Well, here the radius is 1, so the radius would still be 1. And then this would be I times 2 pi n, and that would be times k plus k prime. Maybe it's just easier to think of this as e to the I, and we have a 2 pi n, and that whole thing is times k plus k prime. So is this in our group? And it may not be, right? Remember, what do you have to do to get into our group? You've got to be 2 pi n times an integer. This is an integer that's between 0 and n minus 1. Well, k and k prime are between 0 and n minus 1, but their sum need not be. So we have a little bit of work to do to show that that is, in fact, one of the elements in G. And so to do that, let me just kind of prove it pictorially. Or not prove it, but get an idea. I don't know, suppose we divided it into 8. So this would be one element of G. And we have this would be another one. So it would be 1, 2, 3, 4, 5, 6, 7, and then 8. So this is another element G. So if I add this angle, I have to add all this, to this. My rotation will be more than 360, but perhaps I end up on one of those elements. So that's sort of the idea that the multiple, we may get a multiple that's greater than n minus 1, but maybe it's the same number as this. Don't forget, in the complex numbers, every time we add 2 pi, or 360 degrees, to the argument, to the theta in polar form, we would in fact get back to the same number. So that's what we're going to try to do here. And so how would you know that? Well, you would keep dividing out multiples of 360, if you will, or subtracting away 360 from the angle, and eventually you'll get the same number where the angle would be less than 360. That's sort of another way to think about what these are. These are sort of all the fractions between 0 and 2 pi exactly, right? When k is n minus 1, that's just less than 2 pi. But then the very next one more, add 2 pi k over n would take you back to the same as if you had a 0 degree for your theta. Okay, so note, however, using the division algorithm, what do we know? We have two integers where k plus k prime is just going to be equal to q, what do you call it? S. What do I want to call q? Let's change this s to q. Where k times k prime is q times n plus r, where the division algorithm forces the remainder to be between 0 and less than or equal to 0, less than or equal to n minus 1. Okay, often the division algorithm is stated where the remainder is strictly less than n, but an integer strictly less than n is the same thing as an integer that's less than or equal to n minus 1. So then what do we have? We have that the product e to the 2 pi I times k plus k prime over n. So that's the product of these two elements in G, is e to the I 2 pi qn plus r over n. But by properties of exponents, that's e to the 2i pi. This would cancel, qn over n would just be q, and then times e to the I 2 pi I r over n. But integer multiples of 2 pi I is just, this is e to the 2 pi q I, let me say it this way, e to the, basically this is going to be 1. It's an integer multiple of 2 pi. So this is just, any integer multiple of 2 pi is just 1. And then this is just e to the 2 pi r over n. And that's in our set G because the division algorithm guarantees that that remainder is less than it. So we have closure. What about associativity we took at granted? So as a property to complex numbers. What about the identity? Well, clearly 1 has got to be the identity, but 1 is just equal to e to the 2i pi theta times 0. So 1 can be written as a e to the 2, probably put an n here. But that's okay, because when I multiply it by 0, we get that. So that really means 1 is an element of G. Probably should read that out here. So 1 is equal to e to the 0, which is e to the I 2 pi n times 0. But that's an element of K. What about the inverse? The inverse of e to the I 2 pi n times k is what? Would just be e to the I. Okay, you can certainly say negative, but think about it in our example. Or if you have a rotation of 120 degrees, the inverse would be a rotation of 240 degrees. So the way to get the inverse is you just want to subtract what you have from 2 pi. So it would be 2 pi n minus k all over n. And we note that since k is between 0 and n minus 1, n minus k is going to be between n minus 1 and 0, right? We're not going to subtract anything that's bigger than n minus 1, so that means the smallest n minus k would be 0. But we're also not going to subtract anything smaller than 0. So that would mean that's one example. That's I think in the notes I took care of this. This is actually, and I forgot here. That's for k greater than or equal to 1. And the inverse of 1 is, of course, 1. So certainly what I claimed is the inverse is an element of G. Is it actually the inverse? I proved that in the notes. You can see if you multiply these two, you would just add these two exponents. So you have this 2 pi over n, that would be a factor. You have k plus n minus k, that just cancels. So let me, I don't know if you would show that. But I don't have enough board space. But let me maybe zoom out just a tad. So, if I look at e to the I 2 pi over n, I'll just put the k here, times e to the I 2 pi n times n minus k. I would add those two exponents, e to the I 2 pi n k plus n minus k. This is e to the 2 pi n just times n, or e to the I 2 pi, which is equal to 1, because again, recall that the e to the 2 pi I, what is that? Maybe off on the side, I'll get the definition. That's just the cosine of 2 pi plus I times the sine of 2 pi. And the cosine of 2 pi is 1, and sine of 2 pi is 0, so that's 0 plus, 1 plus 0 times I, which is 1. So that shows that product gives you an inverse, and this element we've seen has to be in the set. So we've got inverse, we've got identity, we've got a group. Does it have n elements? That's the last thing we have to show. It's certainly, by counting, it has at most n elements, but are they all distinct? Right? In other words, here's a list in our group. If we let this typical k go from 0 to n minus 1, we have a list of n numbers, or n complex numbers, but are there any repeats? We want to make sure there's no repeats, so we actually have n elements. So could there be equal? So clearly, the order of G is at most n. Could we have e to the k n times 2 pi I equal e to the k prime n over n, times 2 pi I for k not equal to k prime remember, being in the G, being the set G, the criteria we picked was that the number in the numerator, k, had to be between 0 and n minus 1. So could this happen? So what we're going to do is we're going to prove this by contradiction. So let's assume that, and let's try to derive a contradiction. And what we do is there's something saying they write W log without loss of generality. So if K is not equal to K prime, either we have K is greater than K prime, or K prime is greater than K. So what I'll do is, I'll do opposite of what I did in the notes. We may assume that K is less than K prime. And again, the proof for K prime less than K is in the notes, but really even without the notes, what I'm going to do on the board gives you the same idea of it. So we have this equation. So since K is bigger than K prime, we must have this equation here implies if we divide e to the K minus K over n times 2 pi I would have to equal 1. Just divide by these exponents, and so you would subtract those exponents as a common term of 2 pi I, so you just have, that's not over 2, I'm sorry, that's over n. And so what does that mean? So we have the cosine of 2 pi times this K prime minus K. That's got to equal 1. And then the imaginary part, there's a 0 I here, so the sine of 2 pi K prime minus K has to equal 0. And that's over n. But the only way this could happen is if that K prime minus K over n is an integer. Right? If a multiple of 2 pi is plugged into the cosine function, and that's going to equal 1, what could that be? Well, that could be 0 pi, 1 pi, 2 pi, etc. But then for the sine being 0, and I think that's probably enough, even from this, the only multiple of 2 pi, I guess you could say, well, could n be, this could be a half, right? Because, yeah, so what multiples of, so it could be pi, so it could either be 1 or 1/2, or integer representations with fraction part equal to 1/2. Right? So this is only possible if you have this here being, 0 plus or minus 1/2, plus or minus 1, plus or minus 3/2, plus or minus 4/2 or 2, plus or minus 5/2, plus or minus 6/2, etc. But now, if the sine of 2 pi is going to be 0, the sine is only 0 at 0 pi, so that could also work with, the halves wouldn't work with this, right? So if you put a half here, you get a sine of pi That's 0. Okay, I'm sorry, but the halves, this actually here, this equation here allows this to be, this integer to be 0 plus or minus a half plus or minus 2 halves plus or minus 3 halves. It's the cosine being 1, right? The cosine of pi is equal to -1. So this is only possible if we're plugging in 0 or 2 pi. So right here, this is enough to force the integer to be equal to 0. So while this is true, we don't really need we don't need that argument, because the only way a multiple of 2 pi plugged into the cosine would give you 1 is if that multiple is an integer. So what does that mean? That means that n divides this integer with what? Well, the fact we assume that k prime is greater than k, so k minus k prime is strictly greater than 0. And yet it also has to be less than or equal to k prime, because k is positive. But k prime is less than or equal to 1, less than or equal to n minus 1, which is strictly less than n. So I think if you look hard enough there, you've got a contradiction, right? Because you've got n dividing a positive integer that's less than n. So k strictly less than n is impossible. Again, just to see the contradiction, this k prime minus k, that's a positive integer that divides, that's strictly less than n, but yet n divides it. So how can a number that's bigger than k prime minus k divide it? And so that will complete the proof of our claim that set G is a group under multiplication of complex numbers with exactly n elements. And so that completes the proof. So again, I still have the let G up there from the old board. We have shown that G is an abelian. We haven't actually shown that group with exactly n elements for any positive integer. So I have a few more things to talk about groups, so we'll pick that up in a short lecture, that, as well as maybe work through the matrices, the group of 6 matrices, and show that Cayley table by suitable relabeling is the same as the Cayley table from the symmetries of the equilateral triangle.